So I'm picking this problem to sum, and I want to do a few different solutions to this problem. One of the students in this class picked this problem and did one solution, but I happen to know that this is a famous problem with a few different solutions. And I think it's interesting to see how there can be different solutions for the same problem, some of which are more efficient than others, depending on the exact details of the algorithm and depending on which data structures you use. So before we dive into any of the solutions, let's look at the problem, understand what it's even asking. So it says, write a function that takes an array of numbers. It'll be integers. It'll look like this, 1, 2, 3, 4, and a target number. So there's two inputs, an array and a target. It should find two different items in the array that, when added together, give the target value. So if this was the list and the target was 4, then 1 and 3 added together give you 4. So those would be the numbers that we're looking for. And I think it wants us to return the indices. So the 0th element and the second element are the 1 and the 3, and those give 4. So our output is going to be the location of the elements that sum together to get the target. Indices of these items should then be returned in a tuple or list, depending on your language, like index 1 and index 2. So for us, it'll be, in Java, it'll be an array of ints, but it'll just be 2 ints, and that'll be the 2 indices. For the purpose of this kata, some tests may have multiple answers. Any valid solution will be accepted. The input will always be valid. Numbers will be an array of length 2 or greater, and all of the items will be numbers. Target will always be the sum of 2 different items from that array. So it's not like they're going to be tricky and give us some target that you can't find 2 items that sum together to give you it. But let's try to visualize this problem a little bit. I'll use this rectangle here to denote an array. And in an array, we have various values. Like, let's do 1, 2, 3 here. 1. That'll become 2. That'll become 3. And it's just, since we have more space, let's add more elements to this array. So let's say this is, let's actually put it in various orders here. Let's say 1, 4, 2, 3, 7, 9. Let's say that. So something like that. And let's say that the target is, I don't know, I'm just going to pick something like, let's say 9. So 7 and 2 will be what we're looking for. The target here is 9. So this is sample input. Obviously, the algorithm needs to work no matter what the array is and no matter what the target is, but just so that we can illustrate an algorithm, I want to have some concrete data. So I'm going to call this solution number 1. And I think this is maybe the simplest solution. It's a solution that I would expect to occur to most people. It's the solution that occurred to me first. But it's not the most efficient one. But in order to know that, we need to figure out what this simple solution is so that we can compare the two. So let's not even worry about whether it's efficient or not. Let's just examine the solution, which, if I had to put it into words, it would be compare every pair of numbers, find the pair that sums to the target, and return those indices. So to find every pair, we could have a kind of a pointer that looks at, we'll have this arrow, we'll call this arrow pointer 1, and I'll use this thicker arrow for pointer 2 just so that they look different. So we could start by looking at the first two. And then we could say, so I'm illustrating the algorithm here. I'm going to move these pointers around, and I'm going to talk through what the algorithm would be doing. So basically we'd say, okay, look at the first two. Do they sum to the target? If they sum to the target, we're done. But these sum to 5, so it doesn't sum to 9. So now we would move this arrow a little bit farther. Not like that. How do I move this arrow here? So we'd move this arrow over. And then we'd ask the same question again. Did these two sum to the target? And they sum to 3. So the answer is no, not summing to 9. Move it over a little bit more. Does 1 and 3 sum to the target? Nope, sums to 4. Does 1 and 7 sum to the target? Nope, that's 8. Does 1 and 9 sum to the target? No, it overshoots it, that's 10. So we didn't find it. So now we've looked at every possible pair that includes this first number. So now let's move the first number over, and let's reset the second pointer to here. And you can kind of see the pattern now. We're going to look now at every pair of numbers that involves the number 4. This sums to 6 though, so that's not our answer. That sums to 7, not the answer. That sums to 11, that's not the answer. And that sums to 13, which is not the answer. So we still didn't find it. But now we can look at all the pairs of numbers that involve the number 2. Well, that one's 5. Hey, that one's 9. We found it. We found the number, or we found the indexes for the number. So now we would just return whatever index is getting pointed to by pointer number 1 and by pointer number 2. So that's 0, 1, 2, and 0, 1, 2, 3, 4. So the answer would be 2 and 4, because that's where the arrows are pointing. So if I had to put that into words, it'd be something like create 2 pointers, start them at the 0th and 1st elements in the array, use a nested for loop to move the second pointer through the full array for every time the first pointer moves. If at any time we find the that the two numbers pointed to sum to the target, then return those indices. So that's solution 1. Let's write solution 1. Because now we have some pseudocode. We did an example. We moved some arrows around. That shouldn't be too hard to implement. So this nested for loop is a pretty classic pattern. Maybe some of you have seen it before, but we'll start an outer loop to control that first pointer, that this arrow right here, and that index is going to be called, well, a lot of people will just call it I, and I think that's fine to use that convention. So let's say I equals 0, because if you recall, when we started this illustration, we put it at the beginning, and in our pseudocode, we said start them at the 0th and first element in the list. So let's say int I equals 0, and we're going to go all the way through the list unless we exit early. So let's say while I is less than numbers.length. And of course, we're going to increase by 1 each time. And then every time, so I'm just going to copy this line so that I can have a nested for loop. Every time we increment I by 1, we want our next pointer, which traditionally would be called j, to start at whatever I is, but plus 1, because we don't ever want the pointers to be at the exact same spot. We always have the j pointer 1 after the I pointer. So we'll start it there. J can run up to the length of the array, and we'll increment j at the end. So now we have our basic structure of something that is going to increment two numbers, I and j, in the same way that we were manipulating these arrows as pointers over here in our example. So now, just in case we need some space, I'll make a curly brace, and let's say number 1 is going to be numbers I. That's whatever number is getting pointed to by the variable I. And number 2 is going to be numbers j. Every time I save it, it runs it. I didn't actually mean to run it. I was just trying to save it. It's just muscle memory there. Now we want to ask, we're on this line of the pseudocode, if at any time we find that two numbers pointed to sum to the target, we return those indices. So you can just say if number 1 plus number 2 equals target, then we'll return a new, and we can look down here for the syntax. It's going to look something like this. New int, not number 1 and number 2, we want to return I and j. And then since the instructions say that there will always be an answer in the list, we shouldn't have to do anything outside the loop. But let's just return -1 down here. In some harder problem where we didn't know that the answer, the two numbers would actually be in the array, we might want to do some error handling down here. So let's try this. Right. That's the wrong thing to return down here because we have to return an int array. So let's return basically like this line. But instead of I and j, let's return -1. -1, just something bogus, something that can't be. There we go. Okay, so these tests passed. Let's try attempting it. Okay, so that works. That works. Solution number 1 works. And solution number 1 is fine. There's nothing wrong with solution number 1. In fact, it's very simple. And it uses a classic pattern, nested for loop. Everyone should know this pattern. This comes up a lot. And there are some problems where you will have to look at every pair of some collection because you're looking for two that fit together in a certain way. It's a common pattern that comes up. It just happens to be that with this particular problem, to sum, there's a couple of shortcuts that make it so you don't have to look at every single pair. So you don't have to maneuver these pointers around the whole list until you find the two that sum. There's some cleverer other solutions. So that's the end of part 1 of this video. I'm going to stop it. And what I would recommend is you pause and try to come up with an alternative solution. I think it's actually really tricky, and you might not come up with it. But I think you'll get more out of the next part of the video if you at least try. You just think to yourself, well, how could you find the two numbers that sum to the target, but without doing something like we did in solution number 1? How else could you do it? That's the puzzle. See you in a moment. Okay, let's try a solution 2. Same input, so let me just copy paste that input. We'll use a different area of real estate on this same diagram. So solution 2, if I had to put that into words, is going to be basically, we're going to use a trick, which is we ask ourselves if this data was structured just a little bit differently, would it make our lives easier? And in fact, if the data was sorted, if these numbers went in order, that actually might make it easier to find the 2 that we're looking for. And we'll see that in a moment. But that's the insight here, is that solution 2 is we're going to sort the numbers first, then use 2 pointers, again, just like in solution 1, except there's going to be a difference. But one starting at the beginning and the other at the end. That's the idea. So we're going to flesh that out with an example. So I'll move some pointers around and illustrate it, and then I'll try to write some pseudocode for it. But let me copy a pointer down, because we know we're going to have one pointer at the beginning, and we're going to have another pointer at the end. But like I said, this only works if it's sorted. So let's sort the array first. So 2. So 1 is the least in this one, and then 2 is the next least. I'll put that there. And then 3 is the next least, so put that one there. 4 is the next least, so keep that one where it is. 7 is the next least, and then 9 is the next least. So now these are sorted, which means that pointer 2 is looking at the biggest number in the list, and pointer 1 is looking at the smallest number in the list. So that's interesting. So now what we're going to do is we're going to ask, same question, is what we're pointing at, is it the target? And right now it's not the target, it's 10, right? So it's bigger than the target. So if it's bigger than the target, what we're going to do is take our big pointer, the one looking at the biggest item of the list, and we're going to make it a little smaller. So just to say that again, I'll write it down in a moment, but to say it again, 9 plus 1 is 10. That's bigger than 9, the target, so we decrease our current sum by moving the big pointer down. Same thing now. So this is a loop. This is the second iteration of the same loop. So now we ask again, is 7 plus 1, that's 8, is that bigger or smaller than the target? Well, now it is smaller than the target. So we're going to do the opposite. We're going to move our small pointer up. And now we're going to ask again, is 7 plus 2 the target? Hey, it is. Hey, we already found it. Bam. Pretty fast, right? We didn't have to look at very many pairs, taking advantage of the fact that we can home in on the 2 that we're looking for based on the fact that the list is sorted. So let me write that algorithm down in some pseudocode. So same thing, create 2 pointers, but we're going to start them at the 0th and last elements in the array. And then I'm not going to quite do the same thing here. We're going to say while the numbers pointed at don't sum to the target, if the sum is greater than the target, we'll move the, we'll call it the big pointer. We'll move the big pointer to the left. Move the big pointer left. If the sum is less than the target, move the small pointer to the right. Okay, so now with that in mind, we have another algorithm that we can translate to Java, or any language, right? The whole point of doing this kind of, I call this whiteboarding, even though we're not using a whiteboard, but this is the kind of thinking that programmers would traditionally do on a whiteboard. If we're trying to hash out what's the best solution to this algorithmic problem, we'd draw pictures on the whiteboard and draw arrows and move them around and stuff like that, and scroll out some pseudocode. And then once we're convinced we have the right answer, then we would go write it down. So we've whiteboarded out a solution, second solution. So now let's try writing it again. So we're going to basically translate all of the elements from this picture and the pseudocode over to Java. Let's clear what we have. And let's basically say int big pointer. And that's going to start at the end of the list. So that'll be starting at numbers length -1. And we have small pointers, which is going to start at 0. So we have two pointers now. And we want to say while the numbers pointed at don't sum to the target. So that sounds kind of like a while loop, so let's try that. So we'll say while numbers big pointer plus numbers small pointer is not equal to target, we're going to do that act of moving the pointers around. But how we move it depends on what they do sum to. So I kind of want to copy this bit right here. Let's call that int current sum. And we'll say if current sum is less than target, then what do we do? I guess if it's less than target, we want to move the small pointer to the right. So that means making, in this case, since the small pointer is an integer, we're going to make it bigger. So we'll say small pointer plus plus. And then we want to do the inverse. So if current sum is greater than the target, then we want to make big pointer smaller. So we'll minus minus on big pointer. And we're maybe almost done. Actually, we're not, because the only time we're returning is this. But when we exit this loop, it should be the case that numbers big pointer plus numbers small pointer equals the target. So we should be ready to just return small pointer and big pointer packaged up into an array. Let's try that. All right, well, that seems to work. Let's attempt it on all of the tests. Oh, it didn't work on one of them. I forgot the most important part. In fact, it's not even in the pseudocode because I wrote it up here and forgot it, which is sort the numbers first. That's part of the algorithm. This whole algorithm doesn't work unless you sort everything first. So we sort the array, and then we create the 2 pointers, and then we start them at 0 and go on to the rest. So now sorting algorithms are an interesting topic in and of themselves. And sorting a large array is actually not fast. So this sorting part does take some time. Still, sorting and then doing this algorithm is actually still faster than solution number 1. I'm not going to give a proof of that in this particular video. We have to take my word for it for now. But in order to get it to even be correct, we have to sort first, and I'm just going to use Java's arrays. I think it's array.sort numbers, and I think we need to import array. Yeah, so import Java util array. I think it might be arrays, in which case it's arrays sort. There we go. Well, okay. Still passing the small tests. Let's test it on the big tests. Yes, okay. So now it works. Now it works. So before it was doing the starting from the beginning and end algorithm, but never finding the solution because the numbers were all jumbled up. Okay, so that's solution number 2. Solution number 2. But, like I was saying, there's actually a third solution here that uses a hash map, which you all remember from earlier in the course, uses a hash map, and it's even faster than these. So the fatal flaw of solution 1 is here. It says compare every pair of numbers. That can be a lot. That can be a freaking lot of numbers. Like, for example, let's say, how many pairs are there in a deck of cards? So for every one of the 52 cards, there are 51 potential matches. So that's 2,000 already. So just in a list of 50, there's 2,000 pairs. In fact, there is this, there's a field of mathematics called Combinatorics, which is about counting things. And if we were to ask this question, how many pairs are there in a deck of cards, this is also the same as saying, what is 52 choose 2? Which is close to what we saw before. This is double that. And it depends on if you consider a pair like the Queen of Hearts and the Queen of Diamonds. Is that the same as the Queen of Diamonds and the Queen of Hearts? It depends. So you might get this or double this. But still, point is, it's a lot. And let's say you have a list of 1,000, which is really not that long. 1,000 items in a list, I mean, or an array, that's not, by computational standards, not very much. But what does 1,000 choose 2? Holy crap, right? That's a lot. We're getting up there. And if we get 10,000 choose 2, now we're already up in the, like 50 million, right? So that's a lot. So if your solution has to look at every pair, it has to do maybe 50 million operations on a moderately large list. So that's the fatal flaw of solution 1, comparing all the pairs. Fatal flaw of solution number 2 is sort the numbers first, right? Because same thing. If you have to sort an array of 10,000, it can take some time. Now, there are very clever sorting algorithms that don't require looking at every pair in the list. And so they can actually sort faster than doing this many operations. So solution 2 is still better. But it does have this fatal flaw of you got to sort things first. So you're going to get some slowdown there, even though this loop does a clever thing and converges on the solution without looking at every pair. So you avoid looking at every pair of numbers in solution 2, but you still have to do a lot of work with the sorting. So for part 3 of the video, I want you to ask yourself, here's my hint, you're allowed to use a hash map. But if you do use a hash map, what's the algorithm? How do you find those 2 numbers that we're looking for without having to look at every pair and without having to sort the list first? That'll be solution number 3. And once again, even if you can't come up with a solution, I think you'll get more out of my explanation of the solution if you take a moment to pause the video, sketch out something, sketch out some possible algorithm. Think it through a little bit. So pause the video, and I'll see you in part 3. Okay, let's do our third and final solution here. Same input, so I'll copy that down to here. And this is going to be solution number 3. And my basic description of this is going to be use a hash map to keep track of the numbers we've seen. So we only need to make a single pass through the list. All right, so this one's going to be a little bit different. So before I was illustrating these other 2 algorithms using these arrows, which is just an illustration of an index, like I or J, really. But now we need something else because we have a hash map. We're actually using a new data structure to help us out. So let's grab, so I'll say that this is our hash map. And it's going to start out empty. There's no keys, no values in it. But it's going to sit here, and it's going to be ready for us to add stuff to as we start looping through the list. So we will use one pointer here. I mean, if you're going to look at items in a list, you got to have at least one variable to keep track of what index you're on. So we're going to have one. And here's what we're going to do. We're going to look at the number, and we know the target already, right? We know we're looking for 9. So we're looking at 1, and at that time, right when we're looking at 1, we know the number we would like to be in this list if we were going to meet the target. We know that if there's an 8 somewhere in this list, then that is a solution. So, so we can basically, what we're going to do is look into the hash map. And I know that's a little silly on the first one, but it'll make sense as we start moving through the list. We're going to look in the hash map to see if we've ever seen an 8. Now, of course we haven't. The hash map's empty. It's the very first iteration. But like I said, it'll make sense in a second. So we're going to look at the hash map, no 8. So we're going to say, all right, well, we haven't seen an 8 yet. We don't know that there's not one yet because we haven't looked at the rest of the list. But we're going to record that we saw a 1. So we're going to say, all right, we haven't found what we're looking for, but we know that there's a 1 and that it is going to map to 0. We're going to record the place we saw the 1, the index we saw the 1 at. So we're leaving this 1 behind, but we might want to reference it later in the hash map. So we're keeping this list of memory, of where we saw things. So then we move on. We say, all right, well, let's look at a 4. And we know that if we were going to find a solution with a 4, we would need a 5 to get to 9. So we look in the hash map, haven't seen a 5. So nothing we can really do now except add in, we can say that we saw a 4 at location 1. Okay, so we still haven't found a solution. Well, we can move on, though. We can say, all right, well, we're at 2 now. We know that if we're going to make a solution with 2 to find 9, we would need a 7. So we look in the hash map. We don't look forward in the list. Like, you know that the answer 7 is in here, and I know that because we've solved this a million times. But the computer doesn't know. It's just going through doing its algorithm. And so it's going to look up in the hash map and say, is there 7? And it's going to say, no, there isn't a 7, sadly. But we can record that we saw a 2. We can record that we saw a 2 at location 2. 0, 1, 2. So index 2. All right, keep going. Notice we're not looking at every pair. We're just making a single pass through the list. So for every number in the list, we just do a single calculation. So if there are 10,000 items in the list, we would do 10,000 calculations, not this many. We would just do 10,000 with the algorithm so far. Okay, let's move on. So looking at a 3. We know that for this to work, we would need a 6. We look in the hash map. We don't see a 6, but let's go ahead and just record that we saw a 3 and that it was at index 3, actually. And then we move on to 7, and here's where something interesting will happen. We know that for 7 to be part of the solution, we would need a 2 to get to 9. And now we can look up in the hash map, and hey, look, there's a 2. We've seen a 2. In fact, we saw a 2 at location 2. So now that is one of our, so that 2 right there, that is one of the indexes that we need from our hash map of stored indexes. And then the one we're on right now, which is 0, 1, 2, 3, 4, is the other one. So 2 and 4 are the indexes that we're looking for to sum up to 9. So that is solution number 3, and that is much faster. So let's write that down as pseudocode. So we don't need to sort the numbers first. We do need to create a hash map. Let's start looping through the elements in the array. If the hash map contains an entry for the, I'm going to call it the partner of the number we're looking at. So if we're looking at a 7, the partner would be 2. It's whatever the target is minus the current number. If the hash map contains an entry for the partner of the number we're looking at, return the current index and the hash map's stored index. Otherwise, or else, record the index of the current number in the hash map, where the key is current number and value is its index. All right. So once again, we got another solution. We did an illustration of how the data changes during the runtime of that algorithm, and we captured the logic of what we're doing in some pseudocode. So once again, we're ready to write this in Java or any other language. Let's do it. This, by the way, would be a great time to pause the video and think through how you might code it, and you'll learn a lot if you do that. I'll give you time to do that now. But here we go. Create a hash map. All right, well, how do we do that? So in Java, we say hash map, just call it map, and we have to give it a type. So let's give it a type of integer to integer, and that equals a new hash map, integer to integer. Save it and it has to run. But let's see, it doesn't find hash map. I believe that's because it's what, from Java util hash map? Or is it Java collections? I think that might be right. Let's just get it to compile. It's always good. Always try to keep your code in a state that compiles. Okay, perfect. So it's compiling. It's just telling us wrong answer. That's great. So that means we imported hash map correctly. So we have a map. So we did the first line of the pseudocode, create a hash map. Now start looping through the elements in the array. So let's just do a normal for loop for that. Let's say int I is 0. And then we're going to go until while I is less than number's length, I++, each iteration of the loop. Okay, so we have some structure for looping through the elements in the array, and now we just have this if-else part that we need to capture in Java code. So we'll say if one thing, we'll do this, else we'll do something else. The thing that we're doing is looking in the hash map if it contains an entry for the partner of the number we're looking at. So let's write down what the partner will be. So that is the current numbers I, and it's going to be target minus that. So if partner is in the map, so we'll say map.contains key partner, then we're ready to return the current index, which will be I, and the hash map stored index. So we'll say return, it'll be a line kind of like this one. So we'll return not -1, -1, but I and map.get of, well, the key is the current number, so we're going to get the partner's index. It's the current index we're on, and the partner's index would be the answer. Otherwise, we'll say map.put, and we'll put in our current number, numbers I, along with its index, which is I. I got rid of a curly brace here, I guess, or maybe I just didn't write it in the first place. Oh, yeah, let's see. Okay, well that works on the basic test. Let's try it over here on the big tests. And that works too. So 3 solutions. None of the tests are big enough to really show the fact that solution 3 is faster than solution 2, which is faster than solution 1. But it should be obvious. If you believe that solution 1 has to look at every pair of numbers, and you believe that there can be lots of pairs of numbers, then it should be obvious that solution 1 is going to do a lot more computational work than solution 3, which just has to look at every number once and store things into a hash map. Now, solution 2 was a little tricky because it kind of looked like we were only making one pass through the list, but then there was all of this extra work in the sorting. And so you might ask, wait, is there extra work in some of these operations, like asking if a map contains a key, or getting something out of a map, or putting something into a map? So accessing that data structure, it would be a good question to ask, wait a second, are those efficient? And the answer is they are. They are efficient. It's very quick to check whether a map contains a key, and it's very quick to get something out of a map, and it's very quick to put things into maps. But I'm not proving that in this video. That would be for a data structures class, or you could look up HashMap Java, and it should tell you, because this is the kind of things that that programmers care about. And here it is in the docs. Implementation provides constant time performance for the basic operations get and put. Constant time performance is just a fancy way of saying it always takes the same amount of time, even if there's a ton of stuff in the map. Even if it's a giant map, it still can put and get very quickly. So get and put are fast. Contains key is also fast. So if you're asking yourself, wait a second, are the map operations efficient? Good, you should ask that question. That's the right question to ask. The answer happens to be yes. The docs confirm it, but it hasn't been proved yet. And if part of you is like, hey, wait, I want a proof of that, cool. You should want a proof of that. That would be something you'd learn in a data structures class. You could also look it up online. Why are hash maps fast? Because the hash maps being fast is what makes solution 3 faster than solution 2 and solution 1. But out of scope for this video and for this class, I just wanted to show you that even for a very simple problem, even for a 6th Q problem on Code Wars, there's actually a lot of depth. A lot of these problems have a lot of depth. And what I mean by that is that there are often many solutions, and some of those solutions are better than others in various ways. And it's very common for certain solutions to be more efficient than others. So I hope you enjoyed that. I'll say one last thing, which is that for any algorithm you write, if you're able to do an illustration like this, like on paper, just sketching out your data, showing where your pointers are, moving them around, if you're able to do that, I find that that's when I really understand something. If I can draw a picture of what my algorithm or my data structure will do, that is the moment where I have crystal clear understanding and I can go write the code no problem. If you're a little fuzzy on the picture, then at least I find that it's much trickier for me to write the algorithm. I also just want to say that you're all doing excellently at your Code Wars problems. I've been enjoying watching your videos, so keep up the good work. and I'll see you next time.